We are ECE Team 2024, and we are working on a field agri robot for crop health monitoring. Our sponsor is AgRevolution LLC, and here are the names of everyone that contributed to the project. Here's a little bit about the sponsor. They're a small agri-technology company based out of South Windsor, and their mission statement is to promote sustainable agriculture through innovation and technology. At the beginning of the fall semester, AgRevolution posed us with the following problem. The farming population in the United States is gradually aging and dwindling, but the demand for food is ever increasing. And this is especially the case in times like today where we have a global pandemic. So our solution to this problem is to develop an agri-robot that can be deployed in the field to monitor crop growth and health. This robotic assistance will help decrease the labor costs for these farms, as well as provide data that they can leverage to improve yield and reduce crop loss. The final objective is to create a system that can autonomously collect data. So the home base is going to be a system that initiates autonomous mode. The field robot will then collect images and humidity/temperature data, and it'll store all this data locally on a flash drive. There are 6 main sections of our block diagram. So this was one of the first steps in creating the technical solution. The first part of that block diagram, and probably the most essential, is the microcontroller. We decided to go with the Raspberry Pi 3 Model B. It provides a decent balance of power and price, and it also has a plethora of GPIO that we can use to control sensors as well as take input from buttons. The second part of our block diagram is the power supply. So we decided to go with a homemade battery. It provided the cheapest solution compared to what we were finding online, and it can also be designed to exactly meet our requirements. So we went out and bought a bunch of 18650 cells. We aligned them in the layout as shown here, and we used the battery management system in order to balance the charge. Here is what the final product looks like. This is the exposed interior. And we decided to wrap that up into a plastic sheath just to prevent it from being exposed to the elements and taking any unnecessary damage. You can tell from the following video that we're very cautious when we're working with the battery. As far as sensors, we're using a compass, a GPS sensor, and 5 ultrasonic sensors to provide data about the immediate area, and this will allow us to make decisions on where to maneuver the robot, so around objects or in navigation. In addition to this, we also have 2 cameras on either sides of the robot and a humidity sensor as well. Humidity sensor can collect ambient temperature as well as ambient humidity. As far as locomotion, the mechanical engineering team that we're working with designed the chassis off to the right there, and they also selected a planetary gear motor to satisfy the torque requirements that we need. So we had to find a corresponding DC motor controller, and that will just allow us to provide enough current from the Raspberry Pis in order to achieve the torque that we need. Here's the data transmission system for the project. Like I mentioned, we'll be using 3 Raspberry Pis. One of them is going to be at the home base, and the other 2 are going to be on board the robot. The home base has 3 buttons that allow the user to input different commands. Commands are issued over 900 megahertz radio, and one of the Pis on board is going to process the command, and then if required, it can send further commands over Ethernet cable to the second Raspberry Pi. Pi 1 is going to be controlling all of the sensors, and then Pi 2 is going to be issuing the motor controls to the motors.
The machine vision part of this project is the open source TensorFlow Lite machine learning platform. Firstly, hundreds of pictures are labeled for the platform to learn from. You can see the progress through the loss graph that is created during training. A lower loss means the model will have higher confidence and accuracy. Here we can see the model in use. I am demoing it by just pointing the camera at a picture of a diseased crop where, once detected, just snap a picture and store it for later viewing. The model can detect tomato bacterial spots, tomato leaf mold, tomato early blight, tomato late blight, bell pepper bacterial spot, potato early blight, and potato late blight.
In order to avoid and maneuver around objects, we'll be using those 5 ultrasonic sensors that I mentioned before, and they're positioned at the front of the robot with the sensors on the extreme ends tilted at 45 degrees, and this provides us with a nice array of data about the objects in the immediate vicinity. We'll be using some trigonometric techniques in order to determine the most efficient path around these objects. In order to achieve autonomous navigation, we developed the following algorithm. Sets of coordinates are stored into a GPS text file that represents the path. The algorithm is responsible for reading the current location and determining the appropriate heading to reach the next coordinate in the path. Those diagrams off to the right just illustrate how the heading angles are correlated to the turning radiuses for the motor controls. We started by developing a prototype V1, and that was simply putting everything that we had ordered into a plastic container. You can see a couple of videos of our initial testing. We then moved on to prototype V2, and we simply transferred the entire electrical system from the plastic container we had into this new nice looking chassis, and it provides definitely a more robust system for the environments that we intend to use it in. Here are a couple of videos just demonstrating the various motor controls that we programmed into it. The COVID-19 virus definitely had a strong impact on our progress. We weren't able to use the laboratories in ITE, and furthermore, we weren't able to meet up as one team. So we had to troubleshoot the issues as they came and communicate things electronically, which definitely has its shortcomings. As far as remaining challenges, we would definitely like to refine the GPS precision. We would like to reduce the command latencies. We'd like to have more granular motor controls, and we need to set up all the programs to resolve errors internally as well as launch when the robot is powered on. This project was a pleasure to work on. I think we'll all be coming out of this as better engineers, and please feel free to take a look at our website and let us know if you have any questions, or please give us your feedback.